Thank you a lot, Christian. Thank you, everybody, for joining us this afternoon for this first of our training sessions here. It's my great pleasure to present to you this new product in our line called ePHASORsim, where we expand our range of model sizes and our range of simulation applications towards large grids, towards the transient stability study of large power grids. And so if I can operate this guy here, there you go. So without further ado, what is ePHASORsim? So ePHASORsim is our product for large-scale system studies, which we can simulate in real time, and that has consequences for the type of applications you can have, now that you can simulate a large grid in hard real time. The range of models that we're talking about here cover positive sequence transmission studies or three-phase fully unbalanced distribution studies. In the case of ePHASORsim, as the name of the product itself says, we're dealing with phasors. We're dealing with simulations around the nominal frequency. So we're studying electromechanical transient stability phenomena. And for that, we have a simulation time step of a few milliseconds, not microseconds as you would have for electromagnetic transient, or faster than that for switching studies. In this case, we're talking about milliseconds. On the other hand, we're talking about a large number of nodes in your system. This is the ePHASORsim, ePowerGrid product family, the ePowerGrid product family. And this is how they cover the spectrum of simulation time requirements, time step requirements, versus the size of your model. So, at the fastest times, you have eFPGA-Sim, where you can go down to the hundreds of nanoseconds, up to tens of nanoseconds, to simulate your very fast electronic switching phenomena. But of course, if you're going that fast, you're not going to have a network that is that big. You're going to have a certain number of nodes there. Then we have our eMegaSim product, in which you can develop control. You can prototype your control devices. You can develop electromagnetic transient simulation studies, where you're going with a bigger time step, let's say of 10 microseconds, 50 microseconds, but you're going bigger on the number of nodes. HyperSim is a software that it's another addition to our product line, in which you can perform large-scale power studies, electromagnetic transient studies, okay, and you can scale up to several CPUs in parallel, taking advantage of the natural delay that you have on a transmission line for parallelism. And now, if you need to go to really large-scale networks with 20,000 nodes and even more in the near future, I hope, we have ePHASORsim. Okay, so ePHASORsim, we're talking about a time step on the tens of milliseconds, or maybe a few milliseconds and up, but really large scale networks. Okay, so ePHASORsim, due to the time step and the size requirements that I just showed you, has a number of interesting applications. You can do real-time simulation. You can use it for transient stability studies. Since it gives you a real-time simulation of a power grid, you can embed that on a product for operator training, for example. It can give you a simulation of a real power grid. So you can train operator on real conditions. On the same vein, you can test SCADA systems with ePHASORsim. You can test your distribution systems, distribution studies. It does participate in hardware in the loop. There is a dashed line here for parallel processing, which is something that is it's in the kitchen, but it's not ready out of the oven yet. But that would allow us to bring the performance even further. So that then you now can talk about networks that span maybe a continent, a pan-European grid, for example. Hardware in the loop, yes, it's a characteristic of our products. We do real-time simulation, we do interface with the real world. And ePHASORsim allows you to develop your own models, user-defined model simulation, so that you can test your own controllers, your own components, the power grid, and so on. Okay. So here's just a quick overview of the component library so far. We see here a number of components for ePHASORsim. We do have a few generator models, voltage source, zip model for loads, transmission line excitation system, power stabilizer models, turbine governor, transformer, reactor capacitor banks, and the possibility to develop your own models for now using Simulink blocks that you would interface with ePHASORsim. In terms of the events and actions that can be taken, the network could be fully unbalanced on distribution studies. For transmission studies, is a balanced network. You can simulate open conductor conditions, line tripping, faults at any place on the transmission line, generator outage, load shedding, tap changing, reclosing commands, loss of excitation, and so on. There is a very extensive list of control actions that can be taken during an ePHASORsim simulation. And, oops. Sorry, I think my clicking actions here have skipped one slide. Let me go back to this one. So what is ePHASORsim actually right now? Let me tell you what it is in the simplest terms. Is that you have your Simulink model. You bring into your model this extra block that is the ePHASORsim solver. And you tell your solver, all right, this is my configuration file where you define your network. And the configuration file is either done in a simple Excel spreadsheet, or we can import PSSC version 32 files as well. So that's it. You bring the block into your Simulink model. I'm going to show you an example later. You define where your network configuration is, and you can start your simulation. Your simulation will be running in one of our targets. The target will be driving our solver then and generating data for your use. This slide is just a quick comparison of using ePHASORsim versus using SPS with the Phasor option. It's as part of one of our deployments we had to do that comparison, and it turned out to be interesting. In ePHASORsim, in both situations here you're using Simulink, obviously. In ePHASORsim you are entering your data with your Excel, and in SPS you're editing the circuit with the SPS circuit editor. Some of the options related to can we do transmission systems, can we do distribution and balanced. We support some models. This has a bigger library, but we're catching up. We have tested 20,000 bus 10 millisecond time step in real time. That's one of the largest systems we have tried, and we have not tried more just because we did not have a bigger one. But potentially we could go even bigger. Whereas our SPS Phasor here, we were able to only go up to 200 before it started becoming hard to manage. Takes 45 seconds to compile this big model over here, whereas this model here took 32 minutes to compile in our in RT lab. Loading is also very fast. All of that performance in ePHASORsim is achieved using a single core right now. So that's why I'm saying that once we step into the parallel processing arena, performance can go up accordingly. Right now we are able to extract that much horsepower from a single core. We were able to simulate this network here using 9 cores in SPS. And so that's what I'm saying here. Right now, we do not have yet a way to split the system among cores, but we're going to get there. Yeah, sorry?
Just a quick question. Is this for the same update rate time?
Same 10 milliseconds. The requirement was that both cases operate in real time. Yes. So, performance is really what it is right now for our simulator. It's fast. It's really fast. Here's an example of speed. We had 3 test cases over here where you can see the number of buses. Over here it's about 5,000, about 10,000, about 20,000. And everything else goes accordingly. 1,200, 2,500, 5,000 generators, and controllers and other components. So, when explaining here the computation time, I'm making a distinction between normal and disturbance. This is normal is between switching events, and this is the computational time taken when you have a switching event. So when we do not switch, and we're just running the network without an event that requires without a change of topology there, we can perform 20,000 buses in less than 7 milliseconds. For a 10 millisecond time step, we are well within real-time requirements, with a little bit of time to spare. When there is a switching event, we do not support then we go beyond the 10 millisecond requirements on this network, but we do stay well within the limits for the 10,000 network. So I can confidently say that we can simulate 10,000 nodes real time with switching events, no problem, or 20,000 without those. Okay. Some of the other features of ePHASORsim. ePHASORsim, so as I said, can do 10,000 buses. ePHASORsim is part of RTLab and as such benefits from the other characteristics we have already in our product, such as the compatibility with standard protocols in the power industry, such as IEC 61850, DNP3, C37, OPC, and so on. So right there you see that if you have ePHASORsim running, you can make ePHASORsim speak to the rest of the world using standard communication protocols. ePHASORsim runs in one of our targets, which are equipped with FPGAs and IOs, which further expands your ability to do work with our simulator. Again, these are characteristics that more belong to RTLab proper. But imagine what you could do with ePHASORsim and these characteristics together. So automating tests using Python scripts, using scope view to have more sophisticated display and recording of your results, using lab view to implement control panels, and I will show you a demonstration of that. And some of you have seen it already upstairs, the demo that I'm running with a TestDrive interface. You can modify many of the parameters while the simulation is running. You can change the amount of load, you can apply faults, change your voltage levels, change set points, act on the taps, and so on. You can interface the ePHASORsim simulation with the rest of Simulink, so you can create your own control models and connect them to our simulator, just as you would normally do with Simulink when prototyping a control. And for entering our data, our configuration, we support a simple Excel spreadsheet format, collection of tables, or we can read data from PSSE. Okay, that's a description of the features of ePHASORsim.
Fabio,
this is,
you're halfway through. You have 10 minutes left, okay?
10 minutes, okay. All right. Some of the applications that we have done already with ePHASORsim, this is one we did for a client where inside this block here, we have the ePHASORsim simulation block. in this block over here, we have some DNP3 blocks, so that you can receive data over the network. And inside this other block here, you have IOs. So I can have ePHASORsim running here, generating data that is given to an IO card. And it goes to the client's own devices, to its own hardware. And the results of the client's own hardware, own devices, comes back via the MP3. An example that we did, just a proof of concept of merging ePHASORsim with electromagnetic transient simulation, where we have part of this simple test network running in the Phasor domain, a little glue logic here to transfer from one domain to another, and this part of it here running in the electromagnetic transient domain. So 10 milliseconds here, 50 microseconds over there. Whoops. Sorry. An example of developing an external controller and sending the results of that control to ePHASORsim, collecting the results back and applying it back to your controller. So you can do your control systems over here and interact with ePHASORsim. And here is the demonstration I would like to show now. We have done, not exactly now, almost now. Almost now, sorry about that. Blue, okay. Sorry about that. That is almost not worthwhile to come back to that slide. We had a little demonstration where we had the network, the transmission network of the Quebec province in Canada, and here is a video that shows the. This tool that I'm showing here is not RTLab. This is a tool called RTDMS, which is a tool for visualization of PMU data. So it's a third-party tool. Okay, that tool is a tool for I think it's called RTDMS, Real-Time Dynamic Monitoring System, something like that, which allows you to visualize PMU data, overlay that data on a grid. You can see here that you can display the voltages on a polar diagram. But the data that is being given there is ePHASORsim. We use ePHASORsim to generate this data and send it to this tool as if ePHASORsim was a bunch of PMUs. So we have some blocks inside our RTLab library that allow a signal to be given to the block and be made available to the world as a PMU. We then have a Phasor Data Concentrator that we connected to those PMUs, and that Phasor Data Concentrator is sending data to RTDMS, where you can visualize all of it. So yeah, you can visualize here in table format. Pretty soon we're gonna see what happens when you actually play with the network. So almost there. So here you go. MATLAB, okay, so Simulink, let's see the master block. This is the Phasor block. This is the ePHASORsim. If you double click that block, what you have is just the option to tell where the configuration file is. It will load the configuration file. It will generate those output and input connections automatically. Okay. This is a submodule that has has C37 communication blocks. To send the PMU data. So as you can see, all of those C37 blocks send their data to this PDC software. It's an open software for an open software Phasor Data Concentrator. Right? So you can see that the software thinks he's talking to the Quebec network. And all right, we're getting there. All right. So yeah, anyway, it's RTDMS. We can advance it a little further down, further. Thank you. Okay, back here. This interface here is TestDrive. TestDrive allows you to create control panels in LabVIEW and connect the various controls and scopes and other widgets to signals in Simulink. Okay, and those signals contain some of the signals being generated by ePHASORsim and some of the inputs that we have configured our model to take. So for example, using this diagram, I am able to send commands. For example, I can open a line, or I can change, like right here, I'm changing the tap on a transformer, and I can then go to this other third-party visualization tool and see what happens. So if an operator or if some control device had actually gone and changed that value, how would that look like for your SCADA system? How would that look like for your operators that you're trying to train? Okay, so they would be able to see all those changes, and you could ask them how would you react, and so on. So yeah, sorry the video is a bit long. You can see that this software, alright, this software is pretty good too. If you want to buy, we can license to you as well. No, the important part is this. See, I just opened the line. Look at what happened with the voltages, right? I just opened the line between Montreal and Quebec. And what is happening with our bus voltage profile here? What is happening with our current flow? Right? And all of that happening in real time. So the speed of the events that you're seeing happen there is actually the real speed at which it would occur in real time. And well, you can see the consequence on this visualization tool. Anyways, I guess that the rest of the video shows you a bit more on that vein. But I would be happy to demonstrate that to you as well live upstairs. We have a demonstration where I can play with those signals and show that to you too. So if we can close the video now, Ahmed, and go back to the slides, and I'm going to close the presentation at this point. Just want to leave my conclusion here. Blue. For those who like, you're welcome. No, black, for those who didn't like the blue. Yeah, that was the slide we were before. This is the just a map of the network you just saw there. So, in conclusion, ePHASORsim is our Phasor mode real-time simulation of large-scale transmission distribution systems. ePHASORsim chief characteristic right now is its performance, its flexibility and extensibility that comes with being part of the Power Grid product family. We have demonstrated already the advantages of ePHASORsim in various working scenarios, some of them for customer deployment, some of them for internal house studies. We have tested, done a little prototype of SCADA system testing. We have used it for external control prototyping. We have tested hybrid simulation, and many more. So I conclude my presentation over here. Thank you again for your presence today, and I would be glad to take any questions you may have. Thank you very much.
Thank you, Fabio. So, would there be any question? Yeah, okay.
Guillaume Lanz from EPFL Lausanne. You mentioned sometimes the time spent for a typical iteration in your numerical integration method, I guess. I would like to know which operation is the limiting factor, or say differently, why are you not able to run faster? Is it due to memory access? Is it due to the digital computation core? Or is it due to the fact that you are then transferring data back to the host computer, or something else? I don't know.
Right. Well, since the simulation is running on a single core, the limiting factor for the simulations themselves is not inter-process communication at this point. We're running single core, so we do not have the problem of load balancing and synchronizing the computation. The numerical workload itself is substantial. It involves computing a lot of elements, solving large matrices, and so on. And that's definitely the limiting factor will always be something like this. You'll see something as a limiting factor in your algorithm. you work on it, you make it better, and then something else becomes the limiting factor. And right now, I think we have squeezed a lot of power out of it. So I would say it's 50-50 between, let's say, solving linear systems and computing the equations of the individual models.
I think there was another person asking. Okay.
I am Juan Brandl. I have two questions. The first question is I already worked, had my hands on the ePHASORsim, and two things. First thing, it's really hard to working with the data for the ePHASORsim block. So maybe you can work with Excel or with PSSE, and there maybe will be a possibility to get an easier way to transfer the data to the ePHASORsim block. Because if you want to simulate a 10,000 bar simulation and type in every kind of information in an Excel table, it's
Yes, absolutely. That's a very pertinent question. In all of these that I presented, where is the altering tool? Where is the tool that allows you to alter your base data? And this altering tool for now is just an Excel spreadsheet. We do understand that that's not, obviously not the ultimate altering tool. And we are in the process of conceiving, studying, trying to identify what we want as an altering tool, because it's a very challenging altering tool as well. When you are faced with the task of entering 10,000 buses and connecting all these buses by lines and placing generators and making sure that all the data is valid, all the data is correct, it's not a simple task. It's not just about any interface that will do it. The interface itself is quite challenging. So for now, we do not have a one-line diagram method. We do not have yet an altering tool. But I think, well, that's definitely something that we are in the process of investigating. Where do we go? What are the needs for such a tool, and where do we go from there? Since we decided, well, when you were faced with the problem of giving to the engineers, giving a tool to perform large-scale simulation, you have to start somewhere, and we decided to start via the solver, because while it's not the most convenient way to do it, it's definitely one way to do it. So at least we can do the studies, and then we work from there, and we definitely know that there is certain things to work in that sense.
okay. Thanks. And the second thing was one of the first slides you showed. You said that it's possible to simulate positive frequency systems. Will there be also an option for maybe in the future for negative frequency due to imbalance simulations?
Yeah, well, that we can also investigate. The problem with simulating multiple sequences is not so much simulating the sequence, but of course interfacing the sequences once you have a fault, right? So once you have a fault, if you consult the basic textbooks, they will tell you, oh, just merge the systems, put them in sequence or in parallel or something like that. But what if you have two faults? Then it's not the same story. Even doing that interfacing by itself is a heavy operation to do in the context of real-time simulation. So it's not as simple a problem as it first appears to be. Another possibility would be to just go full three-phase, right? Another possibility is to just go, you know what, we're going to go full three-phase for distribution and transmission. But to be decided as well. So I do not have a definite answer at this moment. Maybe Jean can. But the distribution systems are fully three-phase unbalanced, yeah. But distribution, we have distribution networks fully three-phase. Oh yes, yeah, absolutely. We could go full three-phase. Yeah.
people want to use that feature more in their distribution side, but it could model the complete system using that feature.
John is absolutely correct. I take it back. We do have a P-line model for lines, which could very well be used for transmission lines. We have three-phase loads, which could be fully unbalanced, so it could be used on a transmission context. For example, if you have loads, lines, what else do we need? We have a voltage source in which you could specify them unbalanced. I think the only thing we're missing right now today is a generator model that would be unbalanced. That's the only thing. A machine. If we would have a machine, we have a three-phase machine, positive sequence. If we were to... Yep, that's exactly it, yeah. So if you can do it today, on Tuesday, on ePHASORsim, I would say no. But give me a network connection and I can code something, that's for sure. Okay. It can definitely be done. It can absolutely, most definitely be done. And if there is an interest on it, and that's valid for everybody really. If there is a client interest for a feature, that's what we want to hear. And we have a chance to bring that feature also into the tool.
Okay, so thank you, Fabio.